When we think about liquids, our instinct tells us that they should flow downward, pulled by gravity. But imagine placing a sponge in a puddle of water. Instead of flowing up or staying put, the water goes against gravity and climbs upwards into the sponge. This seemingly counterintuitive phenomenon, where the water defies gravity, is a fascinating example of capillary action, a process that drives the movement of liquids through narrow spaces. Today my group members and I will introduce you to the captivating science behind capillary flow in porous media. Capillary flow refers to the movement of liquid through narrow spaces without the assistance of any external force like gravity. This movement is primarily driven by intermolecular forces, mainly adhesion, which is the attraction force between liquid and solid surface, and cohesion, which is the attraction between the liquid molecules. In porous media, these forces are the main factors which allow the liquid to traverse through the intricate spaces and narrow spaces. Now if I elaborate and talk a little more on porous media, they are solid materials containing an interconnected network of voids or pores. These pores can be filled with fluids, that is liquids or gases. And depending on the pore geometry and distribution, it significantly affects the properties of the medium. Now depending on structure, the pores can be divided into the following four types you can see on the board. The first one being granular. They have discrete particles and voids and they look like this. Their examples include soil and sand. The second one is foam, which contains continuous solid phase and can have isolated or interconnected pores. The third one being fiber matrices. They are random or interwoven fibers with voids in between them, and their examples include paper and textile. The last one being regular arrays. They are precisely engineered, that's why they have uniform pore size. And depending on the pore connectivity, we can again differentiate into two types. The first one being open cell porous media and the closed cell porous media. In open cell porous media, we have interconnected pores like this. And in closed cell porous media, we have isolated pores like this. So overall we can say that in fluid transport, the pore size and geometry significantly affect the fluid flow. To understand flow through porous media, in class we discussed Darcy's law and Brinkman's equation. The interaction between solid and fluid interface was first quantified by Darcy in 1856. In a study of water percolating through sand, Darcy discovered that flow rate was directly proportional to the pressure gradient. This empirical relationship, called Darcy's law, is valid for many porous media. But it also has many limitations. First of it being that it's not valid for non-Newtonian fluids. It's not valid for Newtonian liquids at very high velocities, and it's invalid for gases at very low and very high velocities. Darcy's law also assumed that the viscous resistance between the fluid and solid interface is much larger than within the liquid. This is how the Darcy's law looks, and this is the equation for Brinkman's equation. So, recalling the initial sponge example that I gave where we saw an interesting application of capillary action, I'd like to hand over the presentation to Sushankita where she'll talk about capillary behavior in detail.
As we have seen how Rupali has introduced the flow in porous media, now we are going to see how capillarity flow takes place. What is capillarity flow? What is capillarity behavior? So the prime example of a capillarity flow or a capillarity behavior is of a capillarity tube. When we place a capillarity tube in a liquid such as water or mercury, we see that two forces come into play. That is the cohesive force and the adhesive force. For example, the cohesive force are the forces between the the molecules of the same type. For example, you can see there are the water molecules here, so there is a strong cohesive or cohesion force between them. This is called as cohesion as well as cohesive forces. But when we see there's a intermolecular interface between a molecule of water and the glass surface, it's called as adhesion or the adhesive forces. So cohesive forces help them maintain the shape of the liquid and properties such as viscosity and surface tension, whereas adhesion leads to a phenomenon called wetting, where the liquid is in contact with the solid surface, and it also depends on the cohesive and the adhesive forces. So here is a prime example of what are the cohesive and the adhesive forces. Now getting back to the example of water and mercury inside the capillary tube, we can observe that water forms a concave meniscus when placed inside a capillary tube. This is because the adhesive forces are greater than the cohesive forces in case of water. The water molecules and the molecules on the glass surface bond together, so adhesive forces are greater than the cohesive forces. Whereas in case of mercury, we can observe a convex meniscus. This is due to the forces between the mercury molecules is much more greater than the forces between the mercury molecule and the glass surface. So here we can say that the cohesive forces are greater than the adhesive forces. So these two are the prime examples of cohesive as well as adhesive forces. In the next part, we can observe that how a contact angle or wetting phenomena give rise to some derivations or the pressure difference in between or at the point of meniscus. Getting back with the example of water in a capillary tube, we can see that water forms a concave meniscus with the surface of the glass in the capillary tube, as this is a part of the sphere. And we can see that capillary force acts upward direction with the contact angle cos theta. So when we calculate or the force balance across the meniscus, we observe that the upward pressure is surface tension into force per unit length into the contact angle theta, which is the capillary force acting in the upward direction. The downward pressure is pressure at cross-sectional area pi r square. So when we assume that the meniscus is at equilibrium, we equate this two equations, the upward pressure and the downward pressure, which comes to be p pi r square is equal to gamma 2 pi r cos theta, and we divide the whole equation by pi r square, and if we divide it by pi r square, we get the final equation p into 2 gamma cos theta upon r, which is further used to derive the Lucas-Washburn equation, which is going to be explained by Philip.
So in 1921, the chemist Edward Washburn published his seminal paper, The Dynamics of Capillary Flow, giving a quantitative model describing how surface tension can affect the dynamics of flow in a porous media. So before I get into his quantitative derivation, I'm going to talk about why it's important and when it's applicable. So, as Rupali talked about earlier, the Darcy and Brinkman equations are very effective equations at describing flow in porous media, but that only applies when there's only one fluid. If there's multiple fluids that can't mix, there are interfaces between them, and the pressures at these interfaces due to surface tension can change the dynamics of flow within the system. So that's why Washburn's equation is needed. Now, Washburn's equation only applies when the pores are very small, and because that's the regime where surface tension dominates. You go any larger and other forces like gravity will start to dominate over surface tension. So now that we understand when the Washburn equation is relevant and why it's needed, I'm going to go into Washburn's derivation for the equation. So Washburn started the equation by looking at capillary flow within a pipe, like this. And this pipe will eventually come to represent a pore in porous media. So it has a radius r, it has a length L. This is one fluid, and this is a second fluid, so maybe this is water and air. And of course there's an interface between them. So the next step, Washburn assumed that the Poiseuille flow applied to this situation, which here we have the average velocity within the Poiseuille flow, which is the pressure difference over the length, the radius squared over 8 times the dynamic viscosity. And now what we can do is, in the situation where capillary flow applies, the pressure is completely due to surface tension. So we can use the equation that Sushangita derived earlier, which is this, and we can plug this into the average velocity. And this is the average velocity, which is a length over time, distance over time. So we could say that this is the same thing as dl average over dt. So now we have this differential equation. The next step is to solve it. So once we integrate that function, and there are a lot of steps involved in that, we can eventually get to this equation, which is the classical form of the Washburn equation. So what this does is it describes basically the average depth into the pipe that the liquid has penetrated in a given amount of time. And as we can see from this, the depth penetrated is proportional to the square root of the time. Additionally, we can also, another way of looking at this is if we multiply by the cross-sectional area, which is pi r squared, and multiply this by pi r squared, we have a equation for the volume that's penetrated into the pipe in a given amount of time. So the last step in Washburn's derivation was applying this simple equation for a single pipe to porous media. So it was actually very simple how he expanded it. Basically, what he said is that porous media is just a summation of a lot of pipes, and that each pipe represents a pore. So here we can see kind of a representation of that. And this is an equation kind of just summing up the volume of all the individual pipes. And this gives a way to predict the total amount of fluid that's gone into the porous media in a given amount of time. So for me, this equation seems too simple. Like, there's so many assumptions, and it's hard for me to believe that this even works, but it's been experimentally shown to work in a lot of cases, and scientists after Washburn tweaked the equation to apply to even more situations. Next, Tanmay is going to talk about applications.
Lucas-Washburn equation explains how a liquid penetration depends on the liquid's physical properties and the pore geometry. Now, let's see how it works in real-world applications. Our first example is inkjet printing. When an ink droplet lands on a paper, it penetrates the porous fibers via capillary action. This penetration must be carefully controlled. If ink is absorbed too quickly, it smears and reduces the print clarity. If it's too slow, the ink sits on the surface and it takes longer to dry. Using the Lucas-Washburn equation, engineers optimized ink formation by adjusting properties like viscosity and surface tension. For example, reducing and increasing the ink speed of penetration, while adjusting and ensuring proper interaction with the paper fiber. Next, let us look at oil recovery. In oil reservoirs, oil is trapped within the tiny pores of rocks. During enhanced oil recovery, the fluids, often water or a surface solution, is injected to displace the oil. Capillary forces, modeled by the Lucas-Washburn equation, derives this process. The equation helps us predict the penetration rate of the injected fluid and optimize its composition. By adjusting the pore radius and the fluid surface tension, the engineers maximize the amount of oil extracted. A third example is drug delivery. Porous materials are used in transdermal patches or scaffolds to release the medication into the body. Capillary actions ensures that the drug diffuses steadily through the porous medium and reaches the target tissue. The Lucas-Washburn equation helps us determine how quickly the drug moves by adjusting parameters like the pore size and the viscosity of a drug solution. This allows for precise control over a drug release rate, ensuring effective treatment. To wrap up today's discussion, we have explored the fascinating behavior of fluids as they move through porous media. From the fundamental principles of Darcy's law and Brinkman's equation to the intriguing phenomenon of capillary actions, we have seen how the adhesive and cohesive forces drive capillary flow and how this is mathematically captured by the models like Washburn equation, which helps us predict the movement of fluids through narrow spaces and a wide variety of applications. Whether it's understanding how water rises through sponge, optimizing engine printing, improving oil reservoir, or ensuring precise drug delivery. The principles we have discussed are essential for both scientific research as well as real-world engineering solutions. Capillary actions and the equations we have covered today allow us to better control and design systems that rely on fluid movements through complex, porous materials. From the micro scale of capillaries to large scale of industrial applications, understanding fluid flow is key to making advancement in various fields. Thank you all for your attention. We hope this discussion has deepened your understanding of the mechanics at play in porous media and capillary flow.